I think we're ready to start. So welcome everybody to this presentation. What I'm going to talk about is about security implications in LoRaWAN environments, and I'm going to give you two specific examples that we found during our pen testing. But before we start with the actual talk, just want to talk a little bit about myself. So my name is Manfred Heinz. I'm working with BDO Cybersecurity in Germany, and in our team, we're doing mainly IoT pen testing. So we're doing pen testing of devices which are connected to the Internet of Things, and all the additional things that are related to that, like every IoT device comes with its own web application or web interface with the API. With the API that is connected to that, and all these things. That's what our team is working with. I wasn't in the field of cybersecurity for a long time, so I started 2019, and I actually did different things before that. So I actually studied physics. I did my PhD in physics, and I worked as a defect engineer at the semiconductor industry for AMD and Global Foundries in Dresden and in upstate New York. In Malta, when I did work there, we had the defect analysis software, which was a web application, which was web-based, and that's where my interest for cybersecurity started coming up. I will spare you the details, but you can ask me later on. So, and that's how I found my way into cybersecurity. So, but we want to talk about LoRaWAN environments. So, what I'm quickly going to do with you is I'm going to talk about LoRa and LoRaWAN. I'm going to keep that quite short because I want to focus on the examples that I want to show you. So what is LoRa or LoRaWAN? So LoRa by itself is actually the physical layer. So this is basically just a radio frequency protocol that explains how the modulation works, on which frequency, etc. So I'm not going to talk about that. So I put in two links for you in case you're interested. I think the presentation is shared later on. Is this correct? Yeah. So you can look at these links. The first link is a link to a paper that explains the LoRa modulation in very detail, very mathematical if you're interested in that. The second one is a YouTube video which also explains LoRa really quite nicely, and the video also refers to the presentation in the previous link here. So, but LoRaWAN. So LoRaWAN is a radio frequency standard to transfer data over large areas. So the frequencies used in Europe are 868 megahertz and 433 megahertz. And it can cover very large areas. So in urban environments, it can be 5 to 15 kilometers. And in cities, it's typically about a few kilometers. But you can cover even more larger distances than that for very specific cases. Right, so the data that is typically transferred in LoRaWAN is the data from sensors to some server. We're going to talk about it later on. And LoRaWAN is basically designed for low power consumption. So if you have a sensor with a LoRa controller, then which is battery powered, then the battery life is typically up to 10 years before you have to recharge it or change it. So typical applications here are, you're going to see a pattern here. So everything is smart. So you're going to have smart cities, smart buildings, agriculture applications. So anything can be made smart with LoRaWAN. Exactly. So we're pretty sure about that. Not sure how smart it actually will be. But yeah, you can do a lot of things with it, and you can connect a lot of things and monitor a lot of data. The latest specifications, this is just for your information, is 1.04 and 1.1. There are two specifications here, but currently mostly used is this one, it's the 1.0.4, and the previous version .3 and .2. Just a fun fact, because I already mentioned that it can cover large distances. There has been a record regarding the distance the signal can go. Last year, September 2023, they did track a signal from a fishing boat here in Lisbon, in front of the Portugal coast, in the Canary Islands. So the gateway that captured the signal was on the Canary Islands. So that was like 1,336 kilometers, and that's really impressive for LoRaWAN. That's just a fun fact for you. So how does the LoRaWAN environment actually look like? So on a very high level here. So we have end devices, and the specification covers how the end device talks to the LoRaWAN server, which is here. But the end device can't directly talk to the LoRaWAN server. That's physically not possible because you're using radio frequency on one side and the LoRaWAN server talks via TCP/IP. So you have to somehow bridge that, and that's where the gateways come in here. So you're going to have the end device, you have a gateway, and a LoRaWAN server. That's the core of your LoRaWAN environment. And then you have on top of that all the applications, all the cloud or whatever, wherever you want to use the data or wherever you want to process the data that you've generated. Okay. So, as mentioned before, we're going to focus on the end device, on one end device specifically, and on one gateway. And that's where I'm going to show you the kind of findings that we found here in a end device and in gateway. So before I go into the end device, I have to mention a couple of things about the LoRaWAN, how LoRaWAN communicates. So LoRaWAN uses an application key. This application key is used to derive other keys like the application session key and the network session key, which are then all used together to encrypt the data, to ensure message integrity checks, and to authenticate the actual end device. Because LoRaWAN uses symmetric encryption, you have to make sure that you have the application key on the end device and on the LoRaWAN server. Otherwise, you won't be able to read messages there. So somebody has to go in and type in the app key on the end device and go in and type in the app key on the LoRaWAN server. So the communication doesn't exchange any keys. So we are safe on that base here. So we require secure storage of this application key. It needs to be really secure on the end device. You should not be able to retrieve it from there. And the same thing applies, of course, for the network server, for the LoRaWAN server, not the network server. Of course, the application key must be changeable. That's like with a password. You might want to change it at some point of time. And all end devices, and I really have to emphasize that because it's such a unique finding every time. So all of the end devices need to have the unique application key. So we found several cases already where all of the end devices, and LoRaWAN can have hundreds and even more end devices speaking to one gateway. And we already saw that all the end devices did have the same application key. So if you know the application key for one end device, you basically know everything. It's like in a Windows environment, if every user uses the same password and you know the password from one user, you basically own the whole system. So, and last but not least, of course, the application key should be randomly generated. That's also something that we see on a regular basis, that application keys are derived from the serial number from the end device. They're using default keys sometimes. So these things are basically a no-go. But we all know that, right? You know that. Okay. This is just to give you a quick overview. You don't really have to remember all this, and I'm not going to talk much about that. Just the application key is used to calculate the message integrity check on the initial join request. That's when the end device tells the server, hey, I want to send some messages here, register me please. The other thing, it's used to calculate the network session key, and it's used to calculate the application session key. And then the application session key is actually used to encrypt the actual data that is transferred. And the network session key is actually only used for the message integrity checks. Okay. So, the end device. So, on top, I already list the findings that we have, in addition to the things that I mentioned before. So, application key reuse, I already mentioned that. And on the end device, in this case it was a climate sensor, and it has a LoRa controller on board, and it has also a PIC on board, and of course it has the actual sensor on board. And what you could do here is you could manipulate the firmware of the onboard PIC, and you could manipulate the firmware on the LoRa controller. And I'm going to go into detail why this is bad. So talking about the LoRa controller, this is this kind of chip. That's how it looks like if you look on the board. So the application key needs to be stored persistently on the controller, and it can be changed if necessary. There is a part of the memory that can be read out. You can connect via an UART interface, and you can read out memory from there. There are a couple of commands that allow that, but they only allow it for a certain memory range. So in this case, it's 256 bytes from the address 300 to 3FF. And the memory range below that, you are not allowed to read out. And that's the interesting area. That's where the application key is stored. So we are really interested in that. So, however, we could not read out the key in this way, not via the interface. So what now? Well, we know the firmware that is used is open source, so we can take a look in the internet, we can make a code review, and we can check how does this check actually look like. So this is the code snippet. It's probably a little small for the people in the back, but the main message is it's doing an if clause, and it's checking if the address that you provide with your command is within the allowed range. And if it is within the allowed range, it executes the read operation. If it's not, it just skips over that. So that's the code. So that's how it actually checks it. So how do we get around that? Well, the firmware, the controller allows us to erase the firmware, right? So we can just erase the firmware. And at the same time, it does not erase the memory. So the memory is still there. So the application key is still on the chip. And the bootloader is, of course, still on the chip. And the bootloader wants to help us, right? It offers us, hey, come on, you have a controller, it's not workable without a firmware. Come on, put on a new firmware, and we're all good to go. And it doesn't check the signature of the firmware. So there are already 3 findings in that list, so if you can count them. So how is this possibly exploitable? Well, we take the code, we change it, we remove the if clause, we just keep the one that reads out the memory, we recompile it, and we tell the controller, here, we've got a nice firmware, it's ready to go, and basically by just uploading this new firmware, we bypass the check and collect the application key. So we can just read it out via the UART interface, what we could not do before, and it just sends us back the app key. Thanks to my colleague, Clemens Keil, who actually found that vulnerability. Right, so that was the end device. What about the gateway? The gateway is a very complex device in the infrastructure here. It's my time. Okay. The gateway has potentially many interfaces that could be potentially exploited. I'm not saying that they can, but you have USB, you have Ethernet connection, you have potentially Wi-Fi, you have maybe a mobile connection. It's potentially accessible via the internet if it's not configured properly, and it definitely communicates with other devices and other services. Sorry. So, it's basically just another device like in every other IT infrastructure, right? It's like any gateway, any server in the IT infrastructure. You need to apply the same kind of security measures as you would in your IT infrastructure. So it's not really that much different from that. And of course, you have also in this gateway typically a lot of default credentials that need to be changed, right? Same thing here. We found a lot of devices where they did not change the default credentials. For the gateway that we investigated, what we typically also do is we look at the different kind of services that the gateway provides us, right? We connect to the same IT infrastructure like the gateway, so we are within the same network. And we take a look. Typically, the typical Nmap scan, right? And we look what kind of services are available. So in this case, it was nicely, which seemed nicely protected because we only got one SSH service back, which was okay, not much to go here. But then we logged into the device itself and checked out what does the gateway actually provide as services. And there was one particular service that we did not see before, we did not examine before, and the reason why we didn't see it before will be more clear in the next slides. But however, we did a code review of that service, and the service showed that there is a potential remote code execution possible, right? The service that is at hand here is basically waiting for an HTTP connection and is then used to do firmware upgrades. And it does it in a way that it looks at the HTTP body that you provide, takes that HTTP body and puts it into a string that is used for a command, for a system command. So, however, the IP tables rules, as I mentioned, seem to not to allow to address the service from within the network directly, so only from if you were logged in the gateway itself. So it's not reachable, so the remote command execution vulnerability is not exploitable, right? So it's not really a bad thing. We can leave it like that, ignore it. No, we can't. Spoiler alert. So we take another look at the IP table rules. And interestingly enough, incoming connections are allowed if you provide a specific source port. 1700, yeah, that's what we said, right? 1700, 8883, and 1883. These two, for people who know the ports, is MQTT and MQTTS. So LoRaWAN uses a lot of, often uses MQTT. And the other one is a port that is typically used for an additional step from the gateway to a gateway bridge that does an additional transformation of the data before it finally goes to the LoRaWAN server. So we have two TCP and one ODP ports that we can use. So as long as we define the source port, we should be actually able to access the vulnerable service. Right? So let's try that out. And I have here this little video. Let's hope it works fine. Let's see. So what you can see here, there are two terminals, one on the right side, they're both on the attacker machine. On the right side is basically just a listener, so I'm listening on port 1883 for incoming connections. Whatever happens there. I picked 1883 because that's one of the ports that is allowed from the gateway for outgoing connections. And on the other side, this is the exploit, and this is the actual command that I want to be triggered. So it's a very basic bash reverse shell. And this is the port that I use as source port 8883. So, yeah. That's when I was explaining actually what's showing here. So you're going to have to wait for it to trigger. So let's hope it works. It's a video. It will work. So no surprises here. So it's trying to connect. It's trying to trigger the payload. It generates an error on the gateway. So that's why it takes its time before it actually triggers our payload. And yeah, there we are. And we got the shell. And actually, it's actually a root shell because the service runs as root. So we own the gateway, and from there we can start to explore the endless space of the rest of the IT infrastructure. Thanks to Martin Weisbach. He's the one who actually found the vulnerability, and just last week we wrote the exploit together, so just to be able to show it here. Yeah, so I'm already almost at my end. I'm pretty good in time, I think. My takeaways. So, I've only got 4, but I think they're pretty sum it up. End-device firmware integrity is really important. So the end device, if you have firmware on your end device, you want to make sure that not everybody can just change it, right? You need to make sure that it's properly secured against firmware manipulation. There are tools available for that, so this is not something new. This is already something really well established in the IoT or embedded device area. Here it's definitely very important because you can bypass the app key protections for the example. Gateways are really, really important items or devices within your IT infrastructure. You should treat them as such. And you need to secure them really, really strictly with proper firewall configurations. You need to sanitize the HTTP input. And you need to make sure that the communication, the data flow is encrypted. So I didn't mention that, but the service was waiting for an HTTP call, not for an HTTPS call. So that's something in addition. Device firmware gateway configurations need to be reviewed on a regular basis. So you need to make sure that over time nothing has changed, or make sure that there are no new misconfigurations or any vulnerabilities that suddenly pop up because you've changed something in your environment. And you need to make, and the last point here is that LoRaWAN is an end-to-end, has an end-to-end requirement regarding security. So you have an end device that sends data into your IT infrastructure. We only covered the path from the end device to the LoRaWAN, to the gateway. We didn't even go to the LoRaWAN server. But that data, you don't know how that data is used in the application on the LoRaWAN server. It's typically JSON format. So you really need to make sure that the data that goes into your system is sanitized and looks good. And you need to make sure that other systems in the back do actually take another look at the data and make sure that the data has the correct format. That, again, make sure it's sanitized. Again, we had an example from, I think, Michael Schleppi before, where I think it was the blind XSS, right? Where the XSS went in the front end framework, did everything correctly, but sent out into a third-party application the actually unsanitized payload. So that's something that's not supposed to happen. Yeah. So I'm at the end of my talk now, and I hope you took something away from it. And if you have any questions, I'm still here. And thank you very much. One question here.
Actually, two, if time allows.
Yeah, sure.
So, first question is, from an attacker point of view, if I understand correctly, if you attack the end device, you can impact integrity, because you can,
Right, you can send in any data you want once you have the app key. Yeah.
If you attack the gateway, you can impact availability, because you can just, drop all the packets. If you attack both, you could probably also attack confidentiality.
Mm-hmm. Well, if you have the app key, you already got the confidentiality, because you can, once you have the app key, you can read all the data transferred between the LoRaWAN server and the end device.
You can read on the LoRaWAN.
You can, you can listen over the air to the radio frequency. Yeah.
That was just the first question for. That's just the impact an attacker could have, but what's the threat model? What's the motivation of an attacker to actually do that? Do you have some background on the type of devices, the sensors and so on? I mean, okay, it's not a good security, but is it even worth securing it? Is anybody going to attack it at all?
It depends, right? It depends on the use case, right? If you got a LoRaWAN environment where you only take temperature readings, right, for fun and put them on a website, then the impact is probably not that great. You're gonna get wrong temperature values. But if you have a sensor that checks for open or closed windows or doors or anything like that, right? You're in a company where you want to monitor the process chain, right? The product chain. Then it becomes more important that you actually get the correct data and you don't screw up your whole production, right? So that would be the way to go for, right? So yeah, I did have the same question myself when I started with LoRaWAN. I was like, who cares, right? Who cares? Yeah, but it depends. It really depends a lot on the actual use case where it's used. Yeah.
And if I may, sorry. Just out of curiosity, it's not related to security, more on the physical layer. I mean, I'm used to my garage door opener, and it has like a range of maybe, 30 meters. How come on the same band you're allowed to go up to 1,000 kilometers?
That has to do with the specific way that how the LoRa modulation works. So I'm not really able to explain it in detail, but LoRa is so with a LoRa signal you are actually able to read out the signal below the noise level. So that's really impressive, and it's really unusual because with other modulations you are definitely not able to do that. I'm going to refer you to that mathematical paper that I haven't even read through in whole detail, and can't say I have completely understood it. Right? But yeah, you're not going to get your answers there, I think. Yeah. You go first. I think.
But the gateway, if you own the gateway, the idea is that you broadcast the signal to any gateway. The gateway has it's part of a network, and as long as it's the same network as the end device, you can receive it. But as long as the application key is different, and if you don't know that, there's not much you can do about it, right? Except for using it in a botnet.
No. Well, I think there is a misunderstanding. You have the end device that talks with the gateway over RF, right? Mm-hmm. And the gateway is connected to the rest of your IT infrastructure via TCP/IP. Okay, makes sense. So yeah. So and then from there you can go into your IT infrastructure. That's what I meant with.
But this, a gateway should never be in your internal network, right?
No, it has to be. It has to be because you want to transfer the data from the gateway to the actual LoRaWAN server.
You have your own network. Yeah. Okay, I'm used to public networks where this is not the case.
No.
Makes sense.
Your internal network. Yeah. So, your question.
This is a standard that in IoT to kind of analyze the firmware. Is it really the case if you integrate end devices?
Can you say that again?
You said previously in IoT, it's like the standard is really to investigate the end device before bringing it into production. Is this kind of
This is not a standard, no, definitely not.
There's no fast way, kind of. You have to really look at each end device, analyze the firmware, see if there's something wrong about it.
No. So if the end device is from the same company, it's the same end device, it's got the same firmware, of course, and the same parts put on that, and you can't be sure about that. That's true. So you might have a different LoRa controller actually as physical device on the board than the same device that might have a different chip on that. So no, there is no standard. That's, I think, the first answer to that. So there's no standard. There's no security checks there, at least not that I know of, right? There are a couple of companies that do that, like the bigger ones, that have internal security checks and then in addition do external security checks. That's why we are here. That's what we do. They come to us and we do this, like the internet connected lawn mover or whatever they have in their pocket. But yes, you're right. There are a lot of companies that produce these kind of devices, and there is no real security check. But it's true for other things like routers or any other device that connects, right? Did that answer your question?
Yes.
Okay, thanks. Any more questions? No. Then thanks again for attending the class.